Welcome to this exploration of one of the most revolutionary ideas in physics, general relativity. This theory, developed by Albert Einstein, fundamentally changed how we understand gravity. Instead of thinking of gravity as a force that pulls objects together, Einstein showed us that gravity is actually the curvature of the very fabric of space and time itself. Throughout this presentation, you'll discover how mass and energy warp spacetime, creating what we experience as gravitational effects. For over 200 years, Isaac Newton's law of universal gravitation served us well. However, it had some significant problems. First, Newton's theory suggested that gravity acts instantaneously across any distance, meaning if the sun suddenly disappeared, Earth would know immediately. Second, there was no mechanism explaining how gravity actually worked. Third, this instantaneous action contradicts Einstein's special relativity, which states that nothing can travel faster than light. Finally, Newton's theory provided no framework for understanding what gravity truly is. These issues demanded a new approach to understanding gravitation. Einstein's breakthrough began with a simple yet profound insight called the Equivalence Principle. This principle states that gravity and acceleration are fundamentally indistinguishable. Imagine standing in a rocket accelerating through space. You would feel pressed to the floor, just as you feel on Earth. Einstein realized that the sensation of being pushed to the floor in an accelerating rocket is identical to the sensation of being pulled to the ground by Earth's gravity. This remarkable equivalence became the foundation for general relativity. It suggested that what we call gravity might not be a force at all, but rather something else entirely. Einstein's revolutionary insight was elegantly simple, yet deeply profound. Gravity is not a force pulling objects together. Instead, gravity is the curvature of spacetime itself. Mass and energy warp the fabric of space and time, creating curves and dimples in this four-dimensional structure. Objects don't fall because they're being pulled. They follow the natural curves created in spacetime by massive objects. This was a complete paradigm shift in physics. Rather than thinking of space as an empty stage where gravity acts, we now understand that space itself is dynamic, flexible, and shaped by the presence of matter and energy. To understand general relativity, we need to grasp the concept of spacetime. Spacetime is a four-dimensional continuum that unifies space and time into a single fabric. The three spatial dimensions are length, width, and height, which define where something is located. The one time dimension encompasses past, present, and future, defining when something occurs. Einstein showed that space and time are not separate, independent entities. They are interwoven into a single four-dimensional structure. Events that occur simultaneously for one observer might happen at different times for another observer moving at a different speed. This unified spacetime is what gets curved by mass and energy. The rubber sheet analogy helps visualize how mass curves spacetime. Imagine a stretched rubber sheet representing spacetime. Now place a bowling ball in the center, representing a massive object like the sun. The bowling ball creates a depression in the sheet. If you roll a marble nearby, it curves toward the bowling ball, following the slope created in the sheet. This is similar to how planets orbit stars. The key insight is that more massive objects create deeper curves in spacetime. The curvature extends outward from the mass, gradually becoming flatter with distance. Objects nearby don't experience a pulling force. Instead, they simply follow the natural geometry of curved spacetime, moving along paths determined by the curves created by massive objects. In curved spacetime, objects in free fall follow paths called geodesics. A geodesic is the shortest or straightest possible path between 2 points in curved space. On a flat surface, a straight line is the shortest path. But on a curved surface like Earth, the shortest path between two cities is a curved line called a great circle, which is why flight paths appear curved on maps. Similarly, in curved spacetime, geodesics appear curved from our perspective. Earth orbiting the Sun is actually following a straight path through curved spacetime. The planet isn't being pulled by a force. It's simply moving along the natural geometry created by the Sun's mass-warping spacetime. This elegant concept explains orbital motion without invoking any pulling forces. Einstein encoded his theory into a set of mathematical equations called the Einstein field equations. The equation can be written as g sub mu nu equals 8 pi t sub mu nu. While the mathematics is complex, the meaning is beautiful. The left side, g sub mu nu, represents the curvature of spacetime geometry. The right side, t sub mu nu, represents the distribution of matter and energy. The equation tells us that matter and energy on the right determine how spacetime curves on the left. This is often summarized as matter tells spacetime how to curve, and curved spacetime tells matter how to move. These equations are the mathematical heart of general relativity. General relativity has been confirmed through numerous observations and experiments. Gravitational lensing occurs when light from distant stars bends around massive objects like galaxies, exactly as Einstein predicted. Time dilation shows that clocks run slower in stronger gravitational fields, an effect we must account for in GPS satellites. Perhaps most spectacularly, gravitational waves were detected by LIGO in 2015. These are ripples in spacetime itself, created by colliding black holes billions of light-years away. Finally, Mercury's orbital precession, which puzzled astronomers for decades, is precisely predicted by general relativity. Each piece of evidence confirms that Einstein's vision of gravity as curved spacetime is correct.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.